Morning, everyone. Thank you for joining us for another Gravity Masterclass. My name is Danie and today we'll be discussing the anchor and rigging forces. Today will be a bit different than the previous ones. This will be a bit more mathematical and live rather than a presentation. So I hope you guys enjoyed. I hope you guys learned something. As always, for those of you who are new to Microsoft Teams or haven't attended one of these master classes before, we do encourage you to be interactive and to ask questions or to leave comments. So if you look at your Microsoft Teams screen on the right-hand side, there will be a live Q&A. We are welcome to ask questions. On the top, you'll see there are two tabs, one that says featured and one that says my questions. If you go to my questions and at the bottom, you can type in your name where it says your name optional, and you can ask your questions there. And then at the end of this session, I'll do my best to respond to as many of them as I can. And then as I go along, I can publish the questions, and then everybody in the session will be able to see your questions as well. So if there are questions that I think are worthwhile, I'll share them throughout the session, and then we can have a discussion about them between ourselves as well before we get to the Q&A session. Okay. During this session, of course, you're welcome to contact us before, obviously after as well. If you want to have any more information about Gravity, you're welcome to send an email to info@gravitygh.co.za. If you want to book a course, you're welcome to contact bookings at GravityGH. Or you can visit our website. And Gravity Training is a member company of Gravity Group Holdings alongside Gravity Access, who specialize in access solutions, and Gravity Gear, who specialize in work at height equipment, as well as rigging equipment. You're welcome to follow us on social media as well. And for those of you, again, who are new to this or who have forgotten maybe, all of these sessions will be recorded and then uploaded to YouTube either today or somewhere over the weekend. So if you missed it or you want to show it to somebody else, all the masterclasses we've done previously are also up on YouTube. So if you follow us on Facebook, we'll post an update there when it's uploaded and when it's ready. Okay. So the agenda for today is the physics behind the forces that we encounter during work at height. Now, to keep it simple, we'll focus on the forces on the anchors and the forces generated during rigging. You'll see the two combine quite nicely and quite simply. But to understand that, we'll have to go back a few steps and look at a few physical properties first. So we're going to start with the definition of work in the physical sense, not the colloquial sense. And then we go to energy, potential and kinetic. We'll have a look at the work energy principle, and then we'll define a formula for determining impact force or shock load. If a person falls, how much force can we expect to see? And then we'll have a short tea or coffee break. And then when we come back, we'll have a look at triangles. It might seem weird, but just to recap on the trigonometric functions, because we'll need those when we calculate the anchor forces, as well as when we look at the tagline forces. So that is the agenda. So hopefully you guys find something useful there. As I said, let me just get myself on camera. Here we go. So as I said, this will be a bit different than the ones we usually did, or previous master classes, as I'll have my whiteboard and we'll have a discussion about all these different topics. Okay, I am aware there's a bit of glare on the board right about there, so I'll try and avoid it as far as possible, but please, if you can't see something I've written on the board, just send me a message on the chat, and I'll do my best to rectify that. Okay, so let's start. First up, we have a look at work. Okay, now Again, work has different connotations in the normal English. It's a place we go to earn money, or it's something we do when we exercise or move or anything like that. But in physics, work has a very specific connotation. Okay, so this refers to the force we apply in order to displace an object. Okay, so the force to displace. Now, displacement, I might have to define as well. Displacement is not the same as movement. Okay, so if I have an object, a box or something, on a floor, if I apply a force and that box moves a certain distance, I have done work on that box. Okay. More specifically, this will be important later, if the force I apply is in the same direction as the distance traveled, I'm doing positive work. Okay. If the force applied is opposite the direction of travel, that'll mean negative work. Okay. So the formula we use for work, which luckily is denoted by W, equals the force applied times the distance displaced. Okay. I think I see that. So that's the first important formula that we need to understand. Okay. Let's see. Can you guys see what I'm writing? I hope so. Here we go. Okay. So that's work. The next step we look at is energy. Okay, so I'll write these formulas in the corner so we don't forget about them. The first one, work equals force times distance. Okay, now we have a look at energy. Now, according to our agenda, we'll have a look at two types of energy, the potential and the kinetic. Now, there are obviously a lot more, and chemical and heat and electrical and so forth, but we only care about these two for our purposes. So first of all, we'll have a look at potential energy. We abbreviate that as PE. Okay, so potential energy is the energy an object has due to its position in a force field. Okay, now in our case, for work at height, we work in a gravitational field. So the potential energy of an object is due to its position above the Earth. So the higher above the Earth it is, the more potential energy it has. Okay, it's as simple as that. And the formula for that, which is the second one we'll need, is mgh. Okay, now in this case, the m is the mass of the object, g is the gravitational acceleration. Accelerate. I can't spell acceleration. Anyway, that gives, we use the value of 9.8 meters per second for gravitational acceleration, and then h will be the height above the ground. Okay. Sorry, Johnny, is it blurred or is it in that cleared spot? I think it might be a bit blurry. Let me know. I'll rewrite that somewhere else. Okay, so m is the mass, g is the gravitational acceleration, which is 9.8 meters per second squared, and h is the height above okay, hang on. Seems like we have a bit of an issue with the quality of the stream. So you guys can't see what I'm writing. Hang on. Let me see if I can do this on the PowerPoint perhaps. Let's see if I can get a new slide. Okay, let's quickly check this. If you bear with me for a second. Okay, if I'm out of the screen, can you guys see what it says now? Hopefully if I'm standing still, it works. Okay, so in that case, let's see if we can work with the PowerPoint. And okay, let's test this quickly. Sorry guys, I was hoping we can do the whiteboard. Maybe we'll go back to it in a second if there's a better connection. Sorry guys, I'll share it with you now. Okay, if I do this, is that better for you guys? Okay, do you guys prefer if I use the presentation rather than the whiteboard? Now I have to write with a mouse, it will be a bit less clear, or what's the word? Legible. Okay, let's try and continue with the presentation for now, and then if you guys can't see anything, then just give me a shout. Okay, so where were we? Okay, looks like you guys prefer the presentation. So let me just move my computer a bit. Okay, so are you guys still with me, or should I backtrack a bit about what I've said so far? Well, I'll quickly recap. So, here we are. So, first of all, we have work, which is equal to the force applied times the distance of the displacement of the object. Okay, so meaning if I have a box and I push it this way for a certain amount of distance, then the box ends up there, I have done positive work. If I apply the force in the opposite direction, then of course I do negative work. the potential energy of a object is equal to its mass times the gravitational acceleration times the height of the object above the ground. Okay, so the higher the object, the bigger the amount of potential energy it has. Okay, so let's quickly be more clear about what we mean when we say energy. In this potential energy case, it's quite elegant comparison. So the potential energy, or any energy, is the capacity to do work. So the more energy you have, the more work you can do. In this case, the higher an object is above the ground, the more potential energy it has. Therefore, gravity can perform work on that object, bringing it down. But the higher it is, the faster it can come down, therefore the more energy it will have. Okay, so energy and work are closely related, which we'll see in a second. Okay, then next up, sorry guys, writing with this mouse is a bit tricky, so I'll try and keep it as clear as possible. So then we have kinetic energy. Okay, so potential energy is kinetic energy. Potential energy is the energy an object has due to its position above the ground. Kinetic energy is due to its motion. So the formula for this is 1/2 times the mass of an object times its velocity squared. Okay, so don't worry too much about the symbols and the notation as much. All you have to know is potential energy is the energy it has due to its position above the ground, kinetic energy due to its motion. Now you'll see the potential energy has a mass term and a height term. So the higher an object is above the ground, the more energy, or the heavier an object, the more potential energy. And with kinetic energy, it's the same. The more mass it has, or the heavier it is, the more kinetic energy it has, or the faster it's moving. Okay, so if you have two cars running on the highway, driving on the highway, an 18-wheeler truck versus a Volkswagen Beetle, if they're both driving at 120 kilometers an hour, the truck will have more kinetic energy than the Beetle. Okay, so that's the potential energy and kinetic energy comparison. But we also look at total energy, which is usually just denoted by E, and that's equal to, you might have guessed it, the potential energy plus the kinetic energy. Okay, so what that means is if I'm above the ground but stationary, that means I only have potential energy. Okay, if I'm on the ground and moving, I only have kinetic energy. So we'll discuss this in a bit more detail later on, but if I'm falling, I convert my potential energy to kinetic energy. Okay, so I go from a point, let me draw this. So if I'm above the ground, stationary, there my kinetic energy will be 0, and I'll only have potential energy. Now if I start to fall, if I'm somewhere here, my potential energy and kinetic energy will be equal. Okay, because I'm halfway between where I was and the ground. So I have half the height, so I have half the potential energy, but I have twice the speed, so I have gained my kinetic energy by half. Okay, so when I hit the ground, the H in the potential energy becomes 0, therefore I have no potential energy, but I have now maximum speed, so when I'm here, they switch around and my potential energy is 0 and my kinetic energy is at a maximum, and that's all I have. Okay. So that is a very basic and a very quick definition of the two types of energy. And then the next thing we have to look at before we can really get going with this is then the work energy principle. Okay, so I won't go into the derivation of the work energy principle. I'll just give it to you for reference. What it says is, as we said earlier, that the energy is the capacity to do work. So there is a direct correlation between energy and work. In this case, the amount of work is equal to delta. Now, in mathematics and physics, this triangle symbol means the difference. Okay, so the difference in kinetic energy. Okay, so what that means is the work is equal to the kinetic energy of an object at the end of its life, or the end of its movement, minus the kinetic energy at the beginning, the initial. That's right, the F is final, the I is initial. So the final kinetic energy minus the initial kinetic energy. Okay, that's a law of physics, and I will quickly give you the reason why it's so important for us. And this flows over to our next point on the agenda before we go on a coffee break. And then I'll quickly see if I can get a better way of describing these things to you. So, as we said, if an object is in the air above the ground, stationary, it only has potential energy. Okay, so that means because the kinetic energy is zero, the total energy, as we said earlier, the total energy is equal to the potential energy plus the kinetic energy. But here, the kinetic energy is zero, so all the energy is stored as potential energy. Okay, now this thing falls, and when it hits the ground, now our potential energy is zero because we're on ground level, and all that energy has now been converted into kinetic energy. Okay, so I hope you guys are with me. This is where it gets a bit, not tricky, but interesting. So if you look at this scenario, okay, the initial kinetic energy of this thing is zero, right? So we don't have an initial kinetic energy. But at the end, we have all of it, the maximum kinetic energy. But this energy here has to be the same as the energy there because of the conservation of energy law. We can't lose energy, we can't create or destroy it. So all the energy that we had here has been converted during the fall into kinetic energy. So what I can do here is I can say, well, the work at the end has to be the same as our potential energy at the beginning. Okay? I hope you guys are with me. Right. So what that means is that we now can use the two formulas we had at the beginning, saying that work is equal to the force times the displacement is equal to the potential energy, which we can say is the mass times the gravitational acceleration times the height. Okay, now there is a very important equation for our purposes going forward. So I'll quickly rewrite that. So the force times the displacement is equal to the mass times the gravitational acceleration times the height. Okay, so we have now equated work with potential energy. What that allows us to do is if we solve for F, for the force, meaning if I get force on its own, I divide both sides by the distance, I get the mass times the gravitational acceleration times the height, all divided by the distance. Okay. Now that equation there, we can use to give us an estimation of the force that will be experienced by a falling object. So if I take an object, let's say it's 10 kilograms, and it falls 5 meters, let's say, and it hits the ground and it stops within 10 centimeters, right? So it's soft ground, it falls, it hits the ground, it goes into the soft soil about 10 centimeters. The force I can now calculate. So I can take the mass, which is 10, times 9.8, which is the gravitational acceleration, times the height, which you said was 5, divided by 0.1. Okay, so if we have a quick look at what that sum will be, is we have 10 times 9.8 times 5 divided by 0.1. So that gives us a force of 4,900 Newton, as an example. Okay, so if you're doing risk assessments, and if you are wondering about how strong your structure should be, or your anchor point should be, that is the equation you can use, again, as an estimate. There's obviously a lot of variables in between that make these types of equations or calculations extremely difficult and extremely complex. But for our purposes and for an indication as to the force that you'll face and the preparations you have to cater for, that's quite a good starting point. Okay, so again, apologies for the whiteboard not working. I'll see if I can make another plan quickly. But so we have our definition of work, we have our definitions of energy, we have our work energy principle, and we have our impact force calculations. Okay, so let's quickly have a tea or coffee break. If you have any questions about these things up to this point, please drop them in the chat box. Again, the next bit will actually become a bit more complicated. So if I've lost you somewhere along the line here, please do get your questions in so I can repeat something or clarify something before we continue. All right, let's have a 5-minute tea break. Let's be back at 35 past. Okay, thanks guys, see you now. All right, welcome back, guys. I think I found another program that might make it a bit easier for you to see what I'm writing. So let's see if we can get that going. Okay. So we were at the work energy of the impact force calculations previously, and we discussed the work energy principle and then the calculations for the impact force. So the reason why the impact force is such a big issue is that most risk assessments, most structures only cater for the static force in terms of a person hanging in something or a load being suspended on something. But if a person were to fall, that force becomes exponentially greater in terms of the dynamic impact that it might have on your structure or your tools. Okay, so the first thing I'd like to discuss with you guys is triangles. So I'm going to try and draw a right angle triangle, something like that. Okay. So before we get any further, this will just be a quick recap of high school trigonometry. So let's quickly have a look at it. So if I call this angle here, I'll call that alpha. Well, let's not use alpha. Let's just use A for now. Okay. So that's angle A. If I look from the point of view of the angle A, and I ask you to calculate the sine function of A, right? Then you look at the opposite side of the triangle, which in this case, let's call it O for opposite, and you divide it by the hypotenuse, okay, or the longest side of the triangle. Okay, so that gives us O divided by H. Okay, in the same line of thought, if we have cosine of A, that'll give us the adjacent side divided by the hypotenuse. So adjacent divided by H, and then the tangent of the angle A is equal to the opposite over the adjacent. Opposite over adjacent. Okay, so those are, that's a quick recap of the three main trigonometric functions. We'll use the first two in the calculation of the anchor forces, and we'll use the last one for the tagline discussion. So for this, we're going to use the example of a vertical lifeline or a rigging, perhaps. If you have something like that, okay, so it's a rope connected to two separate anchor points, okay? So we have an anchor point there, anchor point there, and some load at the bottom, okay? That will obviously make an angle here. We'll have another angle, and for this case, I'll call that angle theta, the Greek letter theta, which looks like that. Okay. And now I want to know, okay, but if I have a force or a weight hanging down on this side, how do I know how much force is experienced by that anchor point and how much is experienced by that anchor point? Right. Now, the main concern that we have is that if there's an angle between these two things, the force on those anchor points will be greater than if it was just a straight line. Okay, so if I had something like that, and if the load was just hanging straight down, whatever force was hanging there, 100 kilograms, whatever, will be the same at the top there because there's no angle. As soon as I start to move that block sideways to the anchor, now all of a sudden I have a force that is pulling sideways as well as a force pulling downwards. Okay, so the downwards force in this case will be gravity, and the sideways force will be whatever is keeping it to the side. So if I take the sum of those two forces, it'll be greater than just the gravitational one in the first example. Okay. Now, if you're curious that you can prove that by the Pythagorean theorem, obviously that side plus that side will equal that side, but that side is greater than both of those. Okay. I won't go too much into that. For now, all you have to know is that if there's an angle, the force on these two anchor points will be greater. Okay. So let me just redraw my system. Okay, so in this case, we have our angle and we have our two anchor points. Okay, so here's where it starts getting tricky. I have an anchor point there, I have an anchor point there. There's my node where the things split. Okay. I know the weight that's down here. We'll call that the F subscript L, or the force due to the load. Okay. But here I'll have force number 1 and force number 2. This angle on the left-hand side of my, if I divide this big triangle in half, I'll have an angle of alpha there and an angle of beta there. Now, the reason I'm using the Greek letters is just due to avoid confusion with the normal alphabet. If I ever use a corner or a angle, it becomes a bit confusing. So on the left-hand side, we have angle alpha. On the right-hand side, we have angle beta. And we have this hypotenuse, or the force line, is F1. On the right-hand side, we have F2. So now I want to calculate F1 and F2 in terms of this load force down here, right? So what I have to do is I have to find out what component of how much of that force is in this sideways leg of it and how much of it is coming straight down again. So we refer to this as calculating the components of a force. So we have an X component. Now, so X, I mean left and right, and the Y component meaning up and down. Right. So for me to calculate the components, I use that trig identities we talked about earlier. So sine of alpha will be, if I look at that, sorry, you can't see that. This component is the X component of the force. Okay, so sine of alpha, if I look from this angle to that, I'll get the opposite angle, or opposite side of the triangle, sorry, the opposite side, which is Fx, divided by the hypotenuse, which is in this case F1. If I rearrange this, I can calculate F1 as being equal to the sine of alpha times, sorry, if I want to calculate, Fx is then F1 times sine alpha. Okay, so I have now an expression for Fx. So the X component of that force is the force times sine alpha. And I can do the same argument on the other side, which will give me fx of the right-hand side is equal to f2 times sine beta. Okay, so almost there. Because this system is in equilibrium, meaning it's not moving, this thing isn't swinging, it's not bouncing up and down, then if it's not moving left, it's not moving right, then the force of the left-hand side in the x direction has to equal the force of the other x direction. Okay, might sound obvious, but if that was not the case, this thing will move left or move right. So the fact that it's standing still means those two forces must be equal. Now I can replace these values with these ones, so I can have f1 sine alpha equals f2 sine beta, and if I solve for f1, I get f1 is equal to f2 sine beta divided by sine alpha. Okay, that's step one. Right. So now we have the equilibrium of the x components in terms of f1. So f1 is f2 divided f2 times sine beta divided by sine alpha. If I continue, if you remember this sketch, I won't draw it again, but now we do the same idea with the x direction or the y direction. So because this thing is moving up and down, the load of the force coming down has to be balanced by the forces, the y components of both of these. Okay, so the y components is the same idea. We want to have the adjacent one. We have the x, or the y component of the force is equal to the force times cosine of the angle. Okay, so Fy1 is equal to F1 times cos alpha, and then Fy2 will be F2 cosine alpha. Right. So we can then say that Fy1 plus Fy2 is equal to F load. Okay, meaning that y component plus that y component has to equal this load. But we have expressions for Fy1. So I'll replace Fy1 with F1 cosine alpha plus Fy2 will be F2 cosine beta equals the load. Okay, here comes the trick. This F1 is the same F1 as this one. So we replace the F1 with that expression. So we have F2 sine beta divided by sine alpha, sine alpha times cosine of alpha plus F2 cosine beta equals f of L. Right, so we are getting there. If we then take that expression, we factor out and F2, we are left with sine beta over sine alpha times cosine alpha plus cosine beta equals F load. Okay, so all I've done is I've taken that F2 and that F2 and put them outside. Okay, if I simplify that expression, I end up with sine beta cosine alpha plus cosine beta times sine alpha all divided by sine alpha is equal to FL, right? I want to calculate F2, if you can remember that far back. Now this whole expression at the top is equal to the sine of the two angles summed together. Okay, so sine alpha or sine beta cos alpha plus cos beta sine alpha is equal to sine of alpha plus beta. Sine alpha stays the same. If I divide the load by that, it flips around. So I get F2 equals the load, sorry, not equals, times sine of alpha divided by sine alpha plus beta. Okay, and if I do the same process for F1, I can just substitute this back. F1 becomes then the F of the load times sine beta over sine alpha plus beta. Okay, are you guys still following along? Eric, is that node point fixed? Well, I mean, fixed is that it's balanced between the forces. Okay, so there's it's not fixed by a physical restriction, if I can put it like that. So this node is just balanced between the forces. If you suspend something on a rope like that, that middle point won't move left or right. Okay, so we have an expression for F2 and F1, but and Eric, this is your next, to answer your next question. What if the two points are the same height, which means that angle now becomes the same? The alpha and the beta are now equal. Well, let's have a look at what happens. So if you have F2 equals the sine of alpha divided by the sine of alpha plus alpha, because that angle and that angle are now the same, we then end up with sine of alpha, times load there. So then we end up with sine alpha over sine 2 alpha, and this is just a trigonometric identity. So we end up with, I forgot, sine load. So sine alpha divided by 2 times sine alpha cosine alpha times the load. So that sine and that sine will cancel, and we end up with a function a half times the load divided by cosine of alpha. Okay, so if you have alpha there, let's call the whole angle theta, then you can replace alpha with theta divided by 2, which is the same thing. Okay, so that's the special case where the two anchor points on the same level. You get this special case from the first one, and this will be true for the force on the first and second anchor. So using this calculation, you can now, that's the one that we usually see in rope axes and rigging. If it's 120 degrees, both anchor points will feel 100% of the load, and so forth and so forth. This one is the case if your anchor points aren't at the same height, which is more often than not the case in terms of rigging lifelines and working ropes and so forth. Okay. So the idea is now that we have these two equations, okay, and I'll try and run through the last ones a bit quicker. So the force calculations for the anchor points in the special case and the not so special case. So that is quite the mouthful, but let's keep going. Right. So we have this idea of a force, as in I suspend a work on a lifeline and I take his weight, let's say 80 kilograms on that lifeline or whatever. But now we have to focus on that equation that we had earlier of the impact force calculation, and that force we now have to consider when we're using this load force in terms of fall arrest and in terms of risk assessment and planning. If you have a structure and an anchor point where somebody can fall, you can do this calculation and figure out at what angle is it still safe and it's still strong enough. Because if that angle becomes too big, even though you have an anchor point that's, say, 150 kilograms safe working load or 15 kilonewton braking strength anchor, if you don't watch that angle, this force can very easily exceed that if it's applied in an angle or in a too big an angle. Okay, so be very aware of when you do risk assessments and work out planning or anchor planning, or when you place anchors or ask for anchors to be placed, that you consider how the force will be applied and where it will be applied. Okay. Right. Before we go on, let me just get myself back here. Right. Up until this point, we have discussed the physics, the energy and work thing. The main thing I wanted to get across to you is to get to that anchor point calculation of how the force is divided between two anchors. Okay, now again, there are rules of thumb for how you do this, and there is a conversion how you do that. You can use that calculation then to avoid the angles. We just use the heights and the length, which I'll probably put in the summary if need be. But the main thing is, or the main question now becomes, how do you measure the angles on site, and how do you make sure that you are still within the angle? So there's if you want to do these calculations quickly, there is a simple rule of thumb, quite literally. So if you do that, that's about 30 degrees, that's about 60, that's about 90, and then that's about 120. Well, you can see that. That's about 120, depending on your size of your hands and flexibility and so forth. But that'll give you a good indication of what angles you're working with. So if you're on site and you see a lifeline or a knot or a rigging bridle, that whole calculation works in reverse as well. If you flip it upside down and you have something that's horizontal like that, and you've slung it with two slings up like that, that calculation will still work with these angles. You just turn that sketch upside down and it's still the same thing. Okay, So the last thing I promised I'll talk to you about is the tagline calculations, which is a bit simpler. So the idea here is that if I have a tower and I'm lifting an object, and I'm using a tagline to keep that object a certain distance away from my structure. So there's my tagline operator, there's my top of the tower, and I'm keeping the distance here. Okay, so my load is a certain height and my tower is a certain height. Okay, if we call this distance of the tagline operator from the tower, we call that distance A. Okay, the height of the load is B, the height of the tower is C, and the distance that I'm away from that structure is D. Now I want to figure out how much weight is that tagline adding to my load. Okay, so let me just pause there and explain what I mean by that. A thing that's very often missed or neglected is that if I do a lift and I start to tag the object away from the tower, I'm now effectively pulling down on that object more than I was previously. So that extra downward force translates to my lifting system now having to work harder to counter that extra force. Meaning if I'm using a winch or if I'm using a pulley system, whatever it may be, all of a sudden the guys on the other side now have to start working harder than they usually would have. Okay. So it's important that you consider both of those forces. So if we look at this example again, what we need to figure out is we need to calculate that angle and that angle. Okay, so earlier we had the trigonometric functions tan, which is the opposite side over the adjacent side. Now in this case, we have to work with two triangles. We're going to pretend there's a triangle and we're going to use that triangle there as well. So this triangle, this side is equal to the length A minus the distance the load is away, so that's I minus D. And this is height B, okay? So let's call this angle beta again. So the tangent function of beta equals B over A minus D. Okay, if we call that one alpha, then we have, again, the triangle from that side. Our opposite side will be D divided by C minus B to give us that side there. Okay, sorry, I forgot the alpha. Okay, so let me erase, oh, never mind. So the next step, and this is something I won't go into too much detail, but we now have our two functions, right? So tan of beta is equal to B over A minus D. but that means the angle beta is equal to the inverse of the tangent function of d over a minus b. Oh, sorry, a minus d b. That should be a d as well. Okay, and you can do the same thing for alpha, which we said was dc over b. D C minus B. Okay, so that's how you calculate those two angles. Now, if you have those two angles, and this is where it becomes a bit easier, is we can use a table of factors. Let me quickly share that with you guys. Okay, so if you look at that table, you'll see the top one says tag line angle and the other one says load line angle. Okay, so we have the tag line angle here and the load line angle there. So in our case, load line angle is alpha, tag line angle is beta. Okay, now if you calculate your angles in the way we discussed in the previous screen, then you take those angles and you round them up. Okay, so let's say you add a calculation and you end up with 53 point something degrees for your tagline angle. Then you round up to 55 and you end up with something like 8.53. You round up to 9. And then wherever these two things meet, that is your load factor. Okay, now if we use that load factor, we can then use that load factor to determine our new weight of our load. So then that load factor we calculated was 1.308, and you simply take that factor and you times it by the load that you're trying to lift. Okay, so of course it is obvious that if I times something by 1.3, it'll be more. So in this case, let's quickly have a look at the load factor table again. So if you have a look at this, most of them are 1 point something. So if you are in this area, it's 1.5 times the weight. But look what happens the more you push your angles. All of a sudden, when you get here, you're almost at 7.5 times the amount of weight that you need to lift. Okay, and then above that, it just becomes dangerous. So between all these calculations we've discussed and talked about, it's extremely important that you are very aware that the forces that we apply during work at height and generate during work at height, during a fall, during something bouncing on a rope, something shock loading, somebody pulling too hard on something, depending on the angles that you are working with. And this is applicable to when you do rigging or when you do installations of work ropes, when you do rescues, when you do cableways, any form of work at height. Be very aware of the forces that you're putting onto your anchor points. And as we can mathematically prove, is those forces can become very, very extreme very quickly. So it's very important that the guys who are in charge of the risk assessments and the site establishments and those kind of things are very aware that there are some serious consequences of not adhering to the proper physical laws and not understanding the effects that forces and angles might have on your site and on your structure. Okay, we ran a bit long, I think. So if there are any questions, I assume there might be some. If there's something you might want me to explain again or to go over again, I'll be more than happy to. Is this something that you guys find interesting? Would you like us to do more of these? Is there a topic that you guys want us to rather focus more on rather than this technical mathematical physics stuff? Do you think this type of scientific approach to work at height will help you in your industry and your risk assessment? What do you guys think? That's probably the end of. I'll quickly show you this while we're busy. So get your questions in, guys, before we adjourn. But I'll quickly show you another way of that first example we did with the anchor forces. What we can do is, if you have the equation, let's use the easy one, or use the special case one. If I have the F on the anchor is equal to the F of the force of the load divided by 2 times the cosine of the angle. So in that case, that angle there, I can re-substitute that cosine. So I know cosine alpha is equal to the adjacent side, that side, divided by the hypotenuse, right? So I have the height of my, or the distance, the perpendicular distance from the node point to the anchor point, and divide that by the physical distance of that hypotenuse. Okay, so that's height 1, and then we'll use S for the slanted one, and then you get the same equation, 2 times the physical height divided by the physical distance. So if you don't have a reliable way of measuring the angle on site, if you don't use that little hand shortcut I showed you, and you are not sure of your angles, but you can always measure distances a lot easier. Okay, so you can have a measuring tape, figure it out, and then take it from there. So you can always re-substitute those values back into your calculations if you need to. Okay, any questions, any comments, anything you guys want me to explain again or to rehash, recover, delete? Do you find this valuable? Do you find this interesting? I think for those of you, it is Friday, so I think this is quite a big wake-up, or a nasty wake-up call for many of us before we had our morning coffees. But I think if I'm going to give it about until, what do you guys think, 20 past 10? And then if you guys don't have any questions, we're done, I think. So if you guys are happy, please don't forget our contact information. If you have any questions or if you have any queries, please contact us at info. For training, you can contact bookings, you can visit our website or follow us on social media. If you need any advice, please do feel free to contact us again. We are more than happy to consult. These kind of mathematical approaches, obviously, we do not include in any of our courses, as it's usually a bit too advanced for the practical scope of things. That's why we decided to include it into this this masterclass for you guys as a little extra bonus if you're curious about the physics behind what we do. If you enjoyed it, please send us a message, and we'll see if we can figure out a way to present more of these types of in-depth physical analysis masterclasses. But if you prefer just a bit of theory, or if there's something you have difficulty that you faced on your sites, perhaps something cropped up on your site that you weren't aware of or didn't know how to handle comfortably, send us a message, make a request, and then we're more than happy to create one of these masterclasses specifically for that topic. If it's something that many people struggle with, it's always nice to address real issues from real people rather than guessing about in the dark. Again, just a reminder, these will go up on YouTube as well. If you guys want to review these or revisit this, if there's something you might feel you missed, if there's something you feel you've missed or that I didn't spend enough time on explaining, please do tell me and I'll quickly go through it again. The trig stuff does take some memory games from high school. If you had trig at high school, it's not something that crops up on a daily basis for many of us. Otherwise, if you're happy with the trig stuff, you can always send me your take on it. How do you calculate your forces on site, and how do you make sure your anchor points are strong enough, and how do you use them? All right, Mark, thank you for your comment. I'll publish that, and you can all have a look at that. So Mark says, find it valuable. It's useful for us taking into account that if an object is stuck in the slewing out of crane at substantially increased forces to the load. This has caused crane failure in the past. A little off topic, but important. Now, that's exactly the type of things we're talking about now, is the not the ignorance necessarily, but the people ignoring the additional forces that can be generated by angles, and something that weighs 100 kilograms doesn't always apply 100 kilograms of force. It depends on how you apply that, where you apply that. Right, so it's very important that as I say, the guys doing the risk assessments, doing the planning for your lifts and for your sites, are aware of the physical limitations and the physical implications of how you apply and where you apply forces. Mark says maybe useful for a lifting or slinging course for our operations. Definitely, we'll definitely look into that. And Eric, I'll have to find out for you if we sell the anchor point testers. I don't think we have any in stock at the moment, but if we don't sell them, we'll put you in contact with somebody who does. So send us an email to info@gravity, and then we'll reply on that, and we'll get you the contact details for a hydraulic tester. Yeah, Mark, these forces aren't, or these calculations aren't usually included in the basic lifting and slinging course, as it's many times a bit too advanced with mathematics. But I think it's very important to have your lifting supervisor or your risk assessor or full prediction plan developer, or whoever's in charge of writing your lifting plan, to have them up to scratch and across these types of mathematical implications. Again, guys, apologies for the whiteboard not working. So handwriting on the screen wasn't all that great, but hopefully you guys got the point and could keep up. We might look into doing another one of these, but with proper video, and then putting that up onto YouTube, so it's a bit easier for you guys to follow along and a bit more natural. Right, guys, that's it from my side. If you wish, I'll hang around up until past. That was the time booked out for this masterclass, so I will be available up until 10:30. But I have nothing new to add and nothing more to say. So you're welcome to leave the meeting and enjoy the rest of your day and enjoy your weekend. Remember to stay safe, look after yourself and each other, and please feel free to contact us if you have any questions. Cheers. Thank you.